So we now are conducting our second interview together with Kerstin. Kerstin is leading a research group at the Max Planck Institute for Medical Research in Heidelberg since 2019. She's conducting together with her team research in the field of biophysical engineering of life, and she studied physics and molecular medicine at the University of Erlangen and earned her doctoral degree at the University of Cambridge. She also was a postdoctoral Marie Sklodowska-Curie Fellow. Not sure whether I spelled that right.
Okay, so in your lab, you were working with DNA origami, and our first question is concerning those DNA origami in general, because when we first heard of them, we kind of felt like being transformed into a science fiction movie. So when I got it right, you basically used a single-stranded DNA and a staple strand to bind this DNA strand together at the position you like. But how does this actually work in the lab? Like, what are you actually doing?
Yeah, that's a good question. I mean, when I first heard about it, I felt exactly the same. So I can very much relate to these feelings. And actually doing it in the lab is amazing because it's one of these experiments that rarely fail. I mean, you go to the lab, things go wrong, but DNA origami, once you have a design that actually works, it's extremely reliable. And what do you actually do? So first of all, actually, you don't go to the lab, you sit down and start on your computer, you design the DNA origami, you design the shape that you want in a 3D cut program. So simply you draw the shape that you want. You can then calculate the DNA sequences that you need in order to make that shape. And then you email the table off to the DNA synthesis company, and you received all the DNA sequences that you ordered. And in the lab, you then start to actually just mixing them together with that long single strand of DNA that you talked about. And then you put them into a thermocycler to heat them up and cool them down slowly to give the structure time to find its optimal configuration. And then you have lots and lots of origamis in just a drop of water. So all you do in the lab is literally pipetting and then placing it in a thermocycler.
Oh, wow. So that's
maybe a purification step afterwards.
Okay, wow. Could you then please explain what is the importance of DNA origami in a bottom-up approach to create a synthetic cell?
Yeah, that's a very good question. I mean, DNA origami, when it first came up, it was used to make smiley faces, and that's of course a very nice proof of principle. But the question is, where do we go with it, and what kind of applications are we using it for? And it's really amazing to see in how many different fields applications are coming up. And for me, or what I want to do with my group, is to actually build functional structures for synthetic cells. So why would you do this? I mean, in bottom-up synthetic biology, you would normally say take biomolecules from cells, isolate them, and then put them back together like the pieces of the puzzle with the vision to one day really achieve a transition from matter to life in the laboratory. But I think it's super hard. And I think everyone would agree, it's not an easy task. And because it is so hard, I feel like we have the freedom to be creative and to really use new tools and new materials to build new structures with the same functionality. So instead of putting the pieces of the puzzle back together, just make your own pieces, right? And make them fit from the beginning. And this, I think, is a bit of a different approach to bottom-up synthetic biology. So to not just rely on biological parts, but also use artificial building blocks. So we won't end up with a synthetic cell that looks exactly like life as we know it, but at least it should be compatible and have the same functionality. And this is exactly what I want to do with DNA origami. So replace some of the components inside synthetic cells that are maybe hard to purify or maybe not even possible to purify from living cells, and replace them inside a synthetic cell, and think also of new ways of putting them together and so on to circumvent challenges that we're currently facing with the standard bottom-up approach where you would isolate molecules from cells.
That's really fascinating. So Besides the bottom-up approach, there are also researchers following the top-down process, which basically means removing not necessary parts from preferably simplistic organisms. How do you think will these two approaches be combined in future?
So actually, in one project that is currently running in my lab, we are actually doing this. So we are actually encapsulating top-down engineered bacteria inside bottom-up engineered synthetic cells and kind of use them as synthetic organelles. I think this could be a direction we could go into in the future, and I think that's the nice thing about bottom-up synthetic biology, or even synthetic biology in general, that you're free to be creative and to take solutions as they work, and not be dogmatic about any approach and say, but bottom-up is better than top-down or whatever. I think we have the freedom to combine them, and I think we will. I still think that that cells are simply very complex. I mean, there has been a lot of things accumulated in the course of evolution that we still don't know what they do, and that for me, especially as a physicist, are very hard to understand. So actually, if you know the components of your system, like in a bottom-up approach, you know precisely what you put in. It's still difficult to understand what's happening, but at least it seems a bit more plausible. This is why I personally really like the bottom-up approach.
Okay, and in your doctoral thesis, you worked on the design of DNA-based lipid membrane pores, which mimic their protein-based natural counterparts in form and function. Could you explain where the differences between the synthetic and the natural nanopores are?
Well, of course, the most obvious difference is that a natural nanopore inside a living cell would be made out of protein, and their synthetic counterparts that I built during my PhD were made from DNA. So that's a very, very obvious difference. But then that's looking at the chemistry, right? Now, if we look more at the physical properties and at the function, as I said before, if we look at the function, then they may not actually be that different. I mean, for the pores that we engineered, we could show that they conduct ions, first of all, and that they are even voltage gated or gated, that they can be closed by a ligand. This was shown by other groups, that they can function inside living cells. So many of the features that proteins show can be replicated with a DNA-based system. The crucial part here was to really insert them into the lipid membrane, and this again shows how important it is to combine DNA nanotechnology with other things. In this case, chemical functionalization. So here we had to attach hydrophobic moieties onto these nanopores to really make it energetically favorable for them to insert into the lipid bilayer. It's lots of engineering. We are also, I wouldn't say we are completely there where nature is, right? Like, for instance, in terms of selectivity. So it has been shown that DNA nanopores can be selective for specific types of ions, but reaching that sophisticated selectivity of, say, a potassium channel has not yet been achieved. So there's certainly a goal for the future.
Well, I definitely think that this topic is fascinating. What I wondered about, you also wrote that you created the smallest DNA membrane pore made from a single membrane spanning DNA duplex, and the second smallest pore consisting out of 2 DNA duplexes. Could you please explain to us why we would be interested in create such small DNA membrane pores, and also how they differ from the bigger ones?
Mm-hmm. So yeah, for me, when I created this membrane spanning DNA duplex, at first it was actually a control experiment. Like, if you think about it, if we think about ion conduction through lipid membranes, we always think about hollow channels. So there has to be a hollow a hollow channel for the ions to flow through. If we look for membrane proteins, we look for hollow proteins, right, with some sort of a cavity in the middle that's enclosed by protein, by the protein itself. So for me, making a channel without a channel was, in the first instance, more of a control, right? The structure like this may insert but should not conduct ions. When we saw that it actually did, we realized that the reason for this is that exactly we do have these differences between protein pores and DNA pores, namely the DNA itself is hydrophilic. So it makes sense that the lipid membrane is reorganizing around this pore. So what is happening is there is a toroidal lipid pore forming around this DNA duplex, making a passage for ions between the lipid membrane and the DNA itself. So we have kind of a toroidal pore, and that can transport ions. And if you think about it, you said it's not actually that small, right? It's not it's large enough to transport ions, right? And this is exactly what an ion channel would do. It also transports lipids, by the way. So it can translocate lipids from one bilayer sheet to the other because you form one continuous bilayer. That's also a function that we know from nature, from scramblazes. So yeah, it's a very interesting structure in the end, I think.
I think so too. You just answered my next question. So, okay, thank you a lot for this. What I also found really interesting, that you had a really short explorative project on XNA pores. Just as a background, as an iGEM team, we thought about working with XNAs at the beginning of the project and found out that there are a lot of hurdles. And I just wondered, because of the background, what did you do for as research in this field, and why didn't you continue with XNAs?
Not much. I think it's very exciting direction to go into, and I would really encourage that. You know how it is in a PhD, other things come up. XNA is a lot harder to get a hold of than DNA. The nice thing of DNA is it's one click in the internet away from your lab, basically. So it's easy to get to, it's easy to handle. Unfortunately, I never invested enough time, and I didn't have enough material at that time. But I hope that other forms of nucleic acids, DNA, XNA, RNA, whatever other synthetic forms of DNA will become more readily available, because I think there's lots of opportunities that are coming up with these directions. So I totally encourage you to follow up. There's no fundamental reason why you shouldn't.
Yes, I think we made the experience that it's really hard to get these XNAs, and if you want to get them, they're really at an eye-watering price, which makes it really hard to afford.
So find a good chemist then.
Yes, that's the other option. So how would you in general assess the role of XNAs in future synthetic biology? Because you always hear about XNAs to be extremely stable and that could be used for construction of synthetic cells. What do you personally think about it?
Mm-hmm. I personally think it's a super interesting direction. I mean, I already told you, I want to go synthetic, de novo, build things from scratch. And of course, if you're then using a molecule that is still so present in life as we know it, let's say, then somehow it's a bit of a cheat. So I'm totally up for moving to even more synthetic polymers. DNA is simply a convenient choice, let's say. You mentioned stability. Stability is certainly good, but it comes with a price. It comes with the price of reactivity, right? Life is an out of equilibrium process, so you will have to think about not just stability, but also the possibility to assemble, disassemble, and so on. So I would say disassembly is just as important as assembly, and so it comes with a price. But I'm sure with XNA and so on, you can design structures for synthetic cells that are even more versatile than the ones that we currently have. For some cases, you may want backbone charge like in DNA. For some other structures, you may not want it at all. For applications in a living system, it's of course very, very nice if you have something that is not recognized by the cell itself. That is maybe not degraded by a DNase, by enzymes in the body. So there's lots of reasons to let's say take the more difficult route and actually go for these synthetic nucleic acids.
Okay, that's really interesting. So what would you say, what are the biggest challenges for new compartments in synthetic cells and their creation? I mean, we've heard about different pores in these membranes. Are there big challenges everyone is working on?
Well, I would say the problem is the membrane itself, the compartment itself, right? In most cases, once you form the compartment, it's very hard to manipulate the stuff that's inside it. So once the compartment is formed, even simple operations become difficult, right? If you want to change the pH of a bulk solution, you just flush an acid. If you want to change the pH inside a synthetic cell, you need a pore first and so on, and you add a whole lot of complication. Or you need to select a membrane which is permeable for protons, of course. But you have to think about these things, right? So precise manipulation inside the compartment, and it's not just about pH, it's also about arranging the components in the way that you want, right? Like a cell, it's certainly not randomly organized inside itself, right? Like every component is at the position where it's needed. So I believe that we really need tools to arrange, and new tools to arrange the components that we have inside them on the nanoscale, but also on the micro scale. So in the end, the cell is a micron-sized object. So if you make nanoscale DNA origamis, that in itself is not enough. We also need organization on the micron scale. So yeah, I think these are the challenges when it comes to compartments, is how to manipulate the things inside them.
Okay. As a 3D printing enthusiast, I was especially interested when I read on your webpage that you're also working on 3D printing for synthetic cells. When I think about 3D printing in synthetic biology, this mainly covers biomaterials, for example, synthetic hydrogels or something like this. What can we expect from 3D printing in synthetic cells or for synthetic cells?
I think it's exactly one of these techniques which is good at arranging components on a micron scale, right? For nanoscale, we have DNA origami is pretty good. We have other tools, protein engineering, whatever, that are pretty good. If it comes to arranging components on the micron scale in a reliable way, then I think 3D printing is super cool, especially because in some ways you immediately have a digital twin, right? So you don't just have your physical object, you also have your physical object in the computer in the end, and you can do whole lots of things with that as well. So yeah, I think it's explorative, but I think that 3D printing will be a very nice tool for synthetic biology as well, just like for biology, in fact.
Okay, so I'm really curious what's coming up in the future. Yeah, let's move to the next question. When we heard about synthetic cells, we also thought about hybrid cells. What is the actual state in combining synthetic and non-synthetic parts in a cell?
Yeah, that's very interesting. I think it's an interesting direction to go into, to say give a living cell additional capabilities by including synthetic parts in a way that is a route you could go into with many of the components that, or let's say almost all of the components in principle that have been developed by bottom-up synthetic biology, be it the DNA nanopores, which you could incorporate into living cells, be it some synthetic cells in itself, which you could incorporate in, say, a spheroid or so on. Like how would natural cells react to a synthetic analog in their circumference? Like you could include them as kind of synthetic organelles. These are all directions that are coming up, I think. So there more and more work in these directions is coming out, but it's still in the early days, I would say. So there are lots of interesting things being done, like also engineering, I don't know, motility, like giving a cell which is normally not capable of swimming actively, for instance, giving it a tail and turn it into a swimmer or so. I think these are all very, very interesting directions which combine biology as we know it and engineering or synthetic parts.
Okay, so thank you for that opinion. Let's now step a little bit away from synthetic biology and talk a little bit about the current situation. So in times of COVID-19, everything goes a bit crazy. How does your group handle your work in the lab?
Yeah, I mean, I just started my group, so we opened the lab, closed it again, and now starting to open again. I don't think any one of us would have expected this to come. And of course, it's challenging. I think it's challenging for everyone to different extents and for different reasons, of course. I think we were in the lucky situation that for most of the time, we were able to continue to work in the lab to some extent, at least, and we had stuff to do from home. So from that sense, we had virtual coffee mornings every day at the beginning and so on. So we were trying to keep the community, to keep the small community that we are in a small group, to keep it alive. What I personally am really missing is the other part of science, which is the interaction, like having a group meeting with some cake or a beer after work with the group members. So this is the part that I'm personally really missing, which I find is really important for building a group as well. And also somehow special about science, right? Just talking about science, sitting down over lunch and having a discussion, you know, like these are these informal interactions that are lost a little bit at the moment, and hopefully we can make up for it in the future when the situation improves further.
Yeah, well, that's exactly the point we're missing too, like this atmosphere. Yeah. So let's hope it's getting better soon.
It's challenging for training new students. I mean, it's easy to keep distance if like my PhD students are totally capable of operating every machine, doing every experiment by themselves. They don't need somebody to look over their shoulder. But if you have a new student, of course, like learning a procedure in the lab alone for safety reasons alone, right? It's important to have somebody who is guiding you right there, not with a distance of 2 meters. Right? So, but yeah, we are improving. I think.
Yeah, sounds good. Okay, so another topic that we also find really important is science communication. And we saw that you're the co-founder of Ring a Scientist. How did you come up with this idea, and what do you like most about the program? Like, we thought that it must take a lot of time besides you work in the lab.
Yeah, actually, the reason why we started this was exactly because we didn't want it to take a lot of time to do science communication. So when I was a PhD student in England, I was often visiting schools and so on. It was very much encouraged in the UK, also well funded, by the way. I was visiting schools. I got invitations from schools that were further and further away in Scotland and Jersey or so. And I just, at some point, I had to say, sorry, I don't have time, you know. So I said, but you know what I can do? I could join your class by Skype. I would be happy to do 1 hour of Skype if it doesn't take me 1 day to travel there and travel back. I just spend my 1 hour, and then maybe students still take something away. Then I realized I did this several times, and I realized that the students actually quite liked it, and the teachers liked it because there wasn't much to organize, and the students were very interactive because somehow less afraid to ask questions and so on. So, and I could show the lab, right? I could do virtual lab tours. I could show experiments which I could never take with me. when I actually went to visit the schools. And it was very easy to integrate in a day in the lab because I was just showing the experiment I was doing anyway, right? So it was very well suited, I thought, for my schedule. And I talked about this with other scientists and so on. They said, well, outreach, yeah, it takes so much time, but if I can do it by Skype, sure, I'll do it, right? And this is why eventually, together with my partner Carl, we set up this database where we simply want to make it easy for scientists, but also for teachers to find matching partners, let's say. So if a biology teacher wants someone to join their biology class on DNA, they just go to www.ringascientist.org, and on the profile search, they will find lots of scientists, like hundreds of scientists. Some of them will work on DNA. And then it's very easy via a contact to simply contact that scientist via an online sheet. So with this, it's not much work at all because it's all automated. So there's nothing that we currently have to do. The database is running. People are registering. Every now and then I get a request and I Skype with a school class. I've done through COVID times, even with students distributed in their homes. So I think it's always a nice experience. It doesn't take too much time.
Okay, well, it's an amazing idea. Like, I really like that. Okay, so my final question is, what would you recommend young scientists who would also love to share their work and talk about science in public like you did a lot?
Well, sign up for Ring a Scientist.
Yeah,
it's certainly one way. No, the advice I would give is to pick what they like, right? There's no point in somebody in me telling you, you really have to join Twitter because on Twitter, that's where you need to be. No, if you want to be on Twitter, be on Twitter. If you prefer to make YouTube videos. Just try it out, right? Like, wherever you feel for yourself, the boundary is the lowest. There's no point in putting another belt around you and say, okay, now from now on, every week I have to make a podcast. There is no point in forcing yourself to do things that you're not like 100% doing because you now enjoy doing them, right? Especially if it comes to science communication, which goes beyond our job, right? So we do it more or less in our free time. So it should be something you enjoy doing.
Thank you very much for this advice.
Yeah, thank you in general for the whole interview. I think it's really valuable for us and really helped us to understand synthetic biology a bit more, and also the advices in science communication are really good. Thank you.
Thank you.
Thank you. Good luck with your project.
Thank you.